Right, this is a video on the intermediate value theorem, and for BC calculus and for the AP calculus test, this is definitely an important theorem that's going to come up. There are going to be times that you need to use it, but like a lot of things, it's not going to come up all the time, so we're going to kind of take some good notes in our composition book so we can check on this often to keep refreshing our memories about it. So an important thing, and the reason we just talked about continuity, is in order to use a theorem or apply a theorem, there are generally conditions that have to be met in order to use a theorem. So there's like, if these things are true, then you can follow all this other stuff. Like you can think about the Pythagorean theorem. If you have a right triangle, then a squared plus b squared equals c squared. So that has to be satisfied in order to use the theorem, the other part, a squared plus b squared equals c squared, for example. So same kind of things are true here. The hypothesis, the if, has to be true, and super often the first thing about on the if part, one of the things is if this function is continuous, then yada yada yada. Okay, all these other things are true. So that's the reason we just did continuity, because it's very important. So this is actually going to be that case. The other thing is that some theorems that we have are what we call existence theorems. So they're theorems that just say something exists. They don't tell you how to find it. Okay, so that's what this theorem is. It's an existence theorem. So it's just going to tell you that we know for sure a certain thing is true. Okay, but we don't necessarily know how to find it from the theorem. Unlike the Pythagorean theorem. So the Pythagorean theorem is not an existence theorem. It's one that actually helps us compute things. So when you're working with the intermediate value theorem, again, the first part that's true is that it must be a continuous function, okay? Now the big idea, so basically the general words, okay, because we have the theorem that has all the little technical parts to it and has all the things that have to be exactly true and very precise, and we have to follow that. But in real life, we need to kind of understand what theorems are. We need to understand how they work and why we would use it. So basically an intermediate value theorem just says if it's continuous, it can't skip any values. So if the y values, if you know there's a y value of 2 and there's a y value of 5 and the function's continuous, it's got to have all the values in between 2 and 5. It can't skip anything. That's the main theorem there. And when it's really often used is to prove there's a 0. So often you have a negative value, you have a positive value. Well, now I can guarantee you then there must be a 0 somewhere in between, because zeros are important, okay? So that's basically it. So using fancy if-then statements, we say if a function y equals f of x is continuous, so if the function is continuous on a closed interval, okay? So it has to be true that the function is continuous on a closed interval. Then f of x takes on every value between f of a and f of b. Now remember, a and b were my endpoints of my interval, so f of a and f of b are the two y values that go with those endpoints, okay? So we know that at least once we're going to have all of those things in between. So let's kind of look at it in a picture to get the idea of the intermediate value theorem. So if we just take a kind of generic, like we'll just draw kind of a generic little curve here that goes from here to here. Okay. So from A to B there, so this would be f of a right here, and this would be f of b, because that's my, where my a goes across, where my b goes across. So this is where a is, so that's f of a, and then here's where B is, so that's f of B. That's the y value that goes with the interval with that A and B. So what the theorem says is that if this is if y equals f of x, so this is my function, that curve is my function, then the intermediate value theorem says that somewhere we are guaranteed that there exists a c, so an x value, there's some c value in there somewhere that's between a and b, such that it's true that f of a must be between f and f of b. And actually I drew this really bad, so let me put c way over here because I kind of drew this not very good, but that's all right. This works. So then this would be somewhere there's this value k, a y value that's in between f of a and f of b. So there exists somewhere some c, and c is going to be between a and b, so c is an x value. There's some constant c such that we know that f of c is somewhere between f of a and f of b. Now the way I've drawn it, f of b is on the bottom, so we'll just put f of b here and f of a there. Okay, so if I put a on, it doesn't matter which one is which, but as long as c is somewhere in that interval, then we're guaranteed that f of c, which I kind of labeled as k, somewhere that value exists, that there's definitely that value. So again, if I was looking for a 0, or I'm looking, does it ever equal 5? That's the idea. Okay, so it can't skip anything. Now let's draw it a different way, again, to kind of show how it is to find zeros. So again, if we take our graph, and this time let me do it in blue. So if f of a is down here, say, and then this goes up, and then we have b up here. So here is my f of a, okay, that goes right through there, and then my f of b is up here. So kind of think of a dotted line just showing you there's where that is. Then we're guaranteed that there's a 0 in between, because f of a is negative, down there below the x-axis, and f of b is positive. And so by the intermediate value theorem, if this function is continuous, this y equals f of x, as long as this is continuous, then we must have a 0, because f of a is negative, f of b is positive, so 0 has to be in there somewhere. So that's basically what we say. F of a is negative, and f of b is positive, and therefore we have f of a less than 0 less than f of b. So we're guaranteed somewhere we have a value that's 0. Okay, so that's just kind of a way that we can look at it, and that's again when it's very common to use that. Okay, and we'll use it that way. You'll see this theorem come up quite often for that purpose, because there's reasons that we want to know certain things are 0, and we're going to be able to show that they are. Okay, so let's look at example 2. So example 2 says, does the intermediate value theorem apply on the specified intervals for the function shown below? So the question says, is there a value of x equals c on the interval from -2 to 5 such that f of c equals 1? Well, we don't even have to do anything to answer that question. If we look at this question, well, right now it says, is there a value where f of c equals 1? And there is definitely that value, because you're going to get an answer of 1. The function equals 1 at actually more than 1, or I guess we're going from -2 to 5. So right here, the value equals 1. So yes, we did find that value. Okay, so yes, C exists. There is a place on the interval -2 to 5. There is a place where f of c equals 1. does the intermediate value theorem guarantee that there had to have been that value? And your answer is no. So there happened to be one, but the intermediate value theorem does not guarantee it because, and you can write IVT for intermediate value theorem. I don't normally like you to do a lot of abbreviations, but this one is pretty common, and it's a lot to write intermediate value theorem. So we'll use this one. Intermediate value theorem does not guarantee a value of x equals c on the interval -2 to 5. And then the reason you would give is since f of x is not continuous on the interval, okay? So it's not guaranteed. Doesn't mean there isn't one, because there is in this case, but it doesn't guarantee. Okay, so there was no guarantee I was going to be able to find that with this example. Okay, so in other words, if somebody said, prove or show me that there has to be a value of that f of, there's some c where f of c is 1 on this interval, I could not guarantee that for you. Okay, but there happens to be one, but I can't guarantee it. Okay, because this function doesn't meet the intermediate value theorem. So let's look at example 2, that says B, but I guess technically this is C. It says, does the intermediate value theorem apply on the specific intervals for what is shown below? So we have a different graph. This one's called G. So it says, is there a value of x equals c on the interval from 1 to 6 such that g of 6 equals 3? Well, we're going from 1 to 6. And in that interval, there's definitely no place where g of c equals 3. Does this interfere with the intermediate value theorem? Like, was there supposed to be? Does it guarantee it? Well, again, no. The intermediate value theorem will not guarantee a value where x equals c on the interval from 1 to 6, and that's because and it's because g of c equals 3 is not in the interval. And the interval would be, and we can say for g of x, which is, g of x only goes from 1 to 6. We go from about 1.5, and then at 6 is -1, because g of x goes from -1 to about 1.5. And g of c is not in that interval. Okay, so 3 is not in the interval. That's the reason that one doesn't have it. So the function is continuous from 1 to 6, okay? But the theorem says I can guarantee every y value between f of a, which would be here, and f of b, which would be there, -1 to 1.5-ish, and 3 is not in there. So I have no guarantee for that, okay? So that's another reason it's not guaranteed. Okay, so what 3 things are necessary to apply the theorem? So first thing you have to show is that f is continuous on or of, I guess it's it's continuous on a to b. So the function has to be continuous from the interval a to b, okay? Second thing is f of a doesn't equal f of b, okay? Because if the 2 endpoints are equal, then there's not going to be any values except for the value itself. So we need the endpoints to not be the same. And f of c, the thing we're looking for, must be between f of A and f of B. Okay, so we have to have the y value has to be, it includes that f of c we're looking for, okay? So like in this example, the y values went from -1 to about 1.5. So even though the function was continuous, it didn't work because the thing I'm looking for was somewhere else. And then on this example, we actually found that value, but we didn't guarantee it because the function's not continuous. So we don't know that that would have happened. It might have happened in the place that it was discontinuous, okay, that we covered that value. Another thing, just to talk about this picture, the intermediate value theorem, if we go back to this one, the intermediate value theorem says I will have all the values from here to here. They will all be there. It doesn't mean there can't be other ones. Okay, there could be other values, but at least I know for sure everything between f of A and f of B is there. There might be other values also. All I'm looking for is the existence that the function value exists in between. Okay, so that's another thing to be careful about. All right, let's look at example 3. So this says apply the IVT, intermediate value theorem, if possible, on 0 to 5 so that f of c equals 1 for this function. Okay, so first thing you have to do in order to use the theorem is start to state whether you can. So we would say f of x is a polynomial and thus continuous over all real numbers. You can probably just say continuous everywhere, but probably better to say continuous over all real numbers, okay? So, and I like to say, you could just say f of x is continuous everywhere, but I really like to say how I know it's continuous. I think that's safer for you for like the AP test. So I know it is because it's a polynomial, okay? And all polynomials are continuous. So that's what we're saying. So that's the first thing I'm going to check. Second thing I'm checking is, let's find out what are the two values for f of 0 and f of 5. Okay, so f of 0, we plug in 0, we're going to get -1. If we plug in 5, we're going to get 5 squared is 25, plus 5 is 30 minus 1, 29. And we are looking for those two things to not be equal. So f of 0 does not equal f of 5, so we're good. And then the third thing is we need to say that, and this is sort of the statement that you're going to kind of write down. So in class, we'll write this in our composition books, but this is sort of the statement that sort of encompasses it all. And you just fill in, you know, the blanks with your stuff. So then by the intermediate value theorem, there exists a value c where f of c equals 1 since f of x takes on every value from, now I like to do it this way, so I like to say -1 equals f of 0 less than 1 less than f of 5 equals 29. Because if you look what you've done, you've basically said 1 is between f of 0 and f of 5. But being more specific, you said that those values were -1 and 29. So this is the best way, I think, to write the statement. To make sure you've covered everything, and this is on the interval where c is between 0 and 5, okay? So this statement is sort of this is the statement that we're going to kind of memorize to say, this is how I apply the intermediate value theorem, okay? So I'm just going to say, by the intermediate value theorem, there exists a value c where f of c equals 1 since f of x takes on every value from, And like I said, I like to say you're technically saying from f of 0, f of 0 less than 1 less than f of 5, but I think it's better to go ahead and put what the two values are. And then if you only put the two values, I feel like you're not quite saying the whole theorem. I just think this is a little more robust to say it that way. And then you're saying, when C is, and then on C on the interval 0 to 5, okay? All right, so let's skip this next one, and we're gonna actually go to this example number 5. And then we'll probably do the last parts of the notes in class. So this is the last part of the video here. All right, so a car travels on a straight track. During the time interval from 0 to 60, the car's velocity measured in feet per second is a continuous function. Of course, we know that. If something's driving, the velocity is going to be continuous. The table below shows selected values. So they figured out the velocity at all these various times. Okay, so t is in seconds, velocity is in feet per second. That's another thing we need to start being really, really careful about, and that's making sure all of our units get included correctly. Okay, so for 0 to 60, must there be a time when v of t equals -5? And then justify your answer. Well, let's go ahead and just do the justification as a way to answer and then use that statement that we were talking about, okay? So let's first think through it. As you go from 0 to 60, okay, so this is our A to B, there's my interval. Is there a time t, that would be your C, okay? Is there a time in that interval where we know the velocity had to be -5? Well, if you look right here, we can see that between 35 seconds and 50 seconds, we had -10 and then we had 0. -5 is in that interval. The function's continuous, so we had to have a moment that was -5. So again, we need to state all of our facts. V of t is continuous. Now that's all I have to say because they literally told me that in the problem. They said it's a continuous function. So I don't have to justify why it is. They said it was. So V of t is continuous. Just state that fact. Second thing, V of 35 equals -10 and V of 50 equals 0. So V of 35 does not equal V of 50. That's the next thing that has to be met. Those are different. Now, could you use any of these other values to the side? Yes, because all of them are negative and they all from there to 0 would include -5. Just think it's better habit to just go the smallest interval that, where it's going to work. Okay, so you could use any of those other numbers technically, but I usually use the smallest one that kind of makes sense. So 3, then this is where we're just going to go ahead and write our conclusion. So we're going to say, by the intermediate value theorem, there is a time t. So now we don't say c because they said time. We have actual units here. So there is a time t where v of t equals -5. It's guaranteed on the interval 35 to 50 since, and like I said, I like to write it this way, -10, which equals V of 35, is less than -5, which is less than V of 50, which we know is 0. Okay, and there you go. It's guaranteed. So they told us this time the function was continuous. Sometimes we're going to have to prove it's continuous, and sometimes they're just going to say it's continuous, or it's something we can just state like a polynomial. They're all continuous, so we know it is. Let's go ahead and answer example 6 here, because this is just saying, giving me an example to answer like a multiple choice question that might be reasonable on the AP test, and then we'll do the last examples in class. So G is a continuous function, okay? So this is a table that has some values. They're telling us g is a continuous function. They're giving us a few values here. For what value of k will the equation g of x equals 3/4 have at least two solutions on the closed interval from 2 to 8. So again, going from this interval 2 to 8, when will you have g of x equal 3/4? Okay, so what value of k would give me 2 times when I would get that answer? Okay, these are my choices right here. This is multiple choice, so we're going to figure it out. So if we put 1 there, would 1 guarantee an answer of 3/4 in 2 different places? Well, 3/4 is less than 1. None of the rest of the numbers are less than 1, so that can't be right. That one doesn't work. Good idea on multiple choice, cross things off when they don't work. What about 3/4? Well, 3/4 doesn't really work because I need 3/4 to be in between the things. Okay, so that's not going to work. So 3/4 isn't going to work. I can actually eliminate 3/2 for the same reason I eliminated number 1, right? It's bigger than 3/4. So the answer must be C. So let's think about why that works. This is 9/16, which is less than 3/4. If you have trouble with that, I don't need to change it to a decimal to figure that out. 3/4 and 9/16. 9/16 is just a tiny bit over a half, because 8/16 would be a half. So that's a little tiny bit over a half. This is a whole quarter over a half, so 3/4 is bigger. So 9/16 is smaller, so that means that for sure, like even just from, 4 to 9/16, and then from here to here, 3/4 is going to be included in there. So we know for sure you're going to get 2 solutions, 2 different times that you're going to get 3/4. Okay, so that's an example of answering a multiple choice question with that. All right, so that's it for this video notes. Again, we'll finish the rest of the notes in class.